So the whole concept of complex numbers is when we have trouble taking the square root of a negative number. And I'll demonstrate here. So how does the square root normally work? Right? So for example, if we have the square root of 4, how would we find this? Well, the square root of 4, basically, when we have a square root, we're just asking, right, what times itself equals 4, right? So in this situation, the square root of 4 would be 2 times 2, which equals 4. Super simple, right? Or alternatively, it could also be negative 2 times negative 2, because negative and negative make a positive. Negative 2 squared is also 4. So basically, question mark squared equals this, right? And I just want to make sure you guys know what I'm talking about. So we're going to do some problems real quick. This should be super simple. I just want you guys to solve the square root of 81 and the square root of 21 for me real quick. You can unmute or type in the chat. Does anyone know what square root of 81 and square root of 121 is? Okay, no problem. So let's go over this. So the square root of 81, like I mentioned before, is we're basically asking, oh, Joyce got it. Yeah, 9. So we're basically asking what times itself equals 81, right? And Joyce says 9. So if we check, 9 times 9 does in fact equal 81. So the square root of 81 in this case would be 9. So what about 121? Well, we're also asking what times itself equals 121. And in this case, it would be 11. 11 times 11 equals 121. And you could always check this with a calculator because, square roots are something that are pretty hard for us to do. It requires a lot of calculations for us to do in our head. So usually, if you have a calculator, that's the best method to doing square roots. But now we're going to dive deeper and we're going to try to take the square root of a negative number. So like what we had before, I'm going to do square root of 4, but this time it's going to be negative 4. So a little bit different. And now if we try to do the same method as before, we'll find that it's actually impossible. Sorry. It's actually impossible to do this because what times itself equals negative 4? Well, we could try 2 like before. 2 times 2, but that equals 4, right? And we're still missing this negative. We could try negative 2 times negative 2, but again, it's a negative and a negative, which makes a positive. So we're left with 4 again. And the key is we're missing this negative. So how do we find this negative again? And that lies in something called the imaginary number or the imaginary unit. And that's represented by simply an I. So this is really important. And one of the major rule of this is that I squared equals negative 1. And this is really weird because usually whenever we square a number, for example, 2, we always get a positive number. Even if we square a negative number, we also get a positive number. But with I, it's different. The definition of I is when you square it, you get negative 1. And now this allows us to do many things. For example, if I told you to take the square root of negative 4 now, it would actually just be 2i. Because if we then took the square of this, right? So ignore this for now. If we squared this, it would be 2 times 2, 2 squared, which is 4, and then I times I. And I times I is the same thing as I squared, right? And remember the rule earlier that I just mentioned, I squared is negative 1. That's the definition of I. So here we can see that it's 4 times negative 1, which equals negative 4, which is what we were trying to find the square root of in the first place, right? So this is super cool. We found ourselves a way to find the square root of a negative number, and this actually works for any square root. So, for example, if I wanted to do the square root of 64, do you guys want to try doing this? Square root of negative 64. What do you think it would be? I'll give you guys like 30 seconds for this. Okay, so Jasper said 8i. Does everyone agree? And Lois says 88. So both of you guys got this first part. Yeah, 8. Yes, super close. So both of you said it was 8, which is very close because as you can see, 8 squared, which is how we usually do these, we just square both sides, right? So for example, if I wanted to find what x was in this case, I would just square this whole thing and square this whole thing. And this square and this square root cancels out. So it's just negative 64 equals x squared. And if we say that 8 is x in this case, and we square 8, we actually just get 64, which is really close to what we have. But notice how we have this negative sign, right? And how do we deal with this negative sign? Well, we know that if we ever want to take the square root of a negative number, all we have to do is add I at the end, because when we, or sorry, not at the end of 64, at the end of 8. Because if we square this, we get 8 squared, which is 64, times I squared, which we know is negative 1, which equals negative 64, which is our answer that we're looking for, right? So we can come to the conclusion in simpler terms that I equals the square root of negative 1. And we know this because if we square both sides, I squared equals this, and the square root and this squared cancels out. So I squared equals negative 1, which is what we had before. Therefore, we know that I by itself equals the square root of negative 1. So this is the most basic form of I, and super useful because so far, all of the square roots we've seen is only for positive numbers. We've never been able to find a way to do negative numbers. But now that we have I, we can do whatever we want with square roots, right? So Jasper, you asked it's 8i squared. Yeah, you were correct. It's because 8 squared is 64, I squared is negative 1. So we got negative 64 earlier. All right, let's move on. So let's try solving this equation. So a little bit of algebra. I'll get you guys started on this. Right? So we're solving for z. We know that z plus 36 equals 0. So z squared equals negative 36. So do you guys want to try? What do you think the next step would be to solve this algebraic equation? Okay, so I'll give you guys a hint. It's sort of the opposite of what I did earlier. You remember how earlier when I did this, I tried to cancel out this square root by squaring both sides, right? By squaring both sides. Now, instead of doing that, I'm going to take the square root of both sides. So here, so this is 36. If we take the square root of this and the square root of this square root and this square, it cancels out. So we just get z equals the square root of negative 36, which is familiar. We just worked with negative numbers, the square root of negative numbers earlier, right? So can anyone solve for z in this case? And if you guys have any questions, feel free to ask. Does anyone know what z could be? Okay, good job, Jasper. You said that it's 6i squared. So, although it is true that it's 6i, you see, you added this square, and this is how we would normally solve it, right? We would square both sides, but right now we're just trying to find z by itself, and z would just be 6i. You don't need to put a squared here because we've already gotten rid of the squared when we did it earlier, right? We took the square root of both sides, and If we do the same thing to both sides, it keeps the equation equivalent. But notice for z, if we take the square root of a squared number, it cancels out, and we actually don't have this 2. And we don't have this 2 either. So it's just z equals the square root of negative 36, which is 6i. But yeah, do you guys all get this? Are there any questions? Because I is a relatively new concept, you know. Okay, so if you guys don't have any questions, that's perfect. Let's move on. So this is a little bit more of a complicated problem. We have to think a little more on this one, but let's go through it together. So what is the second power of I? Well, this is relatively simple, right? Second power of I. This is the definition of I. This is what defines I, and this is the whole reason I exists. I squared equals -1. I explained this earlier. Do you guys all get this concept? This is just, it's sort of a fact, you know. It's the definition of I. For example, if I had like something like a right triangle and like a triangle, I know that this is 90 degrees. This is not related to I, by the way, but I'm just showing you what a definition means. This is 90 degrees. And there's not really a reason we have for 90 degrees. This is just how we've defined this angle, right? This straight angle. We've defined it as 90 degrees. So there's not really a reason I squared equals -1. This is simply the definition that mathematicians use in order for us to be able to use I in order to find the square root of negative numbers, like I showed earlier. So that's the second power of I, which we already know. Now, what is the third power of I? I to the third power. And recall that whenever we're taking exponents, it's just I times itself 3 times. So does anyone want to try doing this? I times I times I. If you think you know it, or if you think you can guess it, just type it out. -1, Jasper says. So we know that I squared equals -1, right? So if, for example, we take this I and we take this I and we combine them together to make I squared, well, we still have this one I left over, right? Because it's I cubed that we're solving for. So we know that I squared is -1, but we also have to multiply I. And -1 times any number is just negative of that number, right? So we know that I cubed is -I. So this is pretty strange, you know, because we didn't see a negative number in front, right? Usually, if you don't have a negative number and you multiply by itself, there's no way you can get another negative number down here, right? But this is just the property of I, and this is why I feel like I is so cool. So, next one. What is the fourth power of I? So I to the fourth power equals I times I times I times I, because you're multiplying, oops, sorry, you're multiplying it by itself 4 times, right? So does anyone want to try this? It's just multiplying I one more time than last time. And here for reference, I'm going to put down I cubed equals -I. Any idea, guys? Jasper, Joyce, Lloyd? We're multiplying I cubed by another I. So we're just multiplying this. We're just adding another I. So what do you think this would be? So, yes, actually, it would just be I squared times I squared, right? And another way of thinking about this is because we put this I and this I together, which forms I squared, and we multiply that by this I and this I, which forms another I squared. So this is actually a perfect way of describing it, because now we can just go back to our initial property that we explained earlier. I squared equals -1. Another I squared also equals -1. So what is -1 times -1? That's just 1, right? So we know that I to the fourth power is actually just -1. It goes back to a positive 1, right? So these next questions, in reality, they rely on the fact that there's a pattern. And let me just show you right here. Well, I to the first power is just I, right? What's I to the second power? We know that it's -1. I to the third power is, from here, -I. And then I to the fourth power is just 1 again. So what if we keep going? What if we get I to the fifth power? Well, whenever we have one extra exponent here, all we do is multiply this by another I, right? So I to the fifth power in reality is just I to the fourth power times I, which is 1 times I, which is I. And if this is I, then we know that I to the sixth power is just I to the fifth power, I to the fifth power times I, which is I times I, because we know that I to the fifth is just I. And we know that I times I is I squared, which is -1. So I'm going to clear all this for now so that we can see more clearly. So I to the fifth is I, and I to the sixth is just I squared, which is -1. What's I to the seventh? Well, I to the seventh is just I to the sixth times another I, right? Which is -1 times I, which equals -I. Same with I to the eighth. That's just -I times I, which equals 1. And if you recall, what did we have earlier? We have I to the first equals I to the second equals -1, I to the third, I to the third equals -I, and I to the fourth equals 1, right? And if we compare these, they're actually the same thing. And what we can conclude from this is that this pattern actually repeats every 4 numbers as the exponent, right? So when we reach 4, it hits 1 again, and then after another 4, we reach 1 again. And if we kept going, right, I to the sixth, or I to the ninth, I to the 10th, all the way down, when we hit I to the 12th, we'll also get 1 again, because that's just in repetitions of 4, right? 4 plus 4 is 8, 8 plus 4 is 12, and this equals this equals this. So this is the pattern. I don't know if I explained this really well. Do you guys understand what I'm getting at here? The pattern? Do you guys understand the pattern? Okay, good. So now that we've established this pattern, we can just use it to solve these next two. So the 8th power and the 284th power. So let's do the 8th power first. Well, we know that I to the 8th, how I would solve this is, since we know that every 4 exponents, it repeats, I would just divide this exponent by 4. So I would just do I to the power of 8 divided by 4, which is 2. Because, or sorry, you would not, you would take the remainder actually of this. So for example, if I took 8 and divided by 4, which is how many times it repeats, then we get 2 with a remainder of 0, right? It fits into, if 4 fits into 8 perfectly 2 times. And this means that it repeats its cycle 1 time, its cycle 2 times. And we know that at the end of each cycle, it's negative, it's just 1, right? Because I to the 4th power is 1, and I to the 8th power is also 1, right? And so by doing this, we can see that the remainder actually tells us which part of the cycle we're on. So for example, I to the 5th, I to the 6th, I to the 7th, and I to the 8th. How do I solve all of these? Well, for I to the 5th, I would divide 5 by 4, and I would get 1 with a remainder of 1. And this remainder of 1 tells me that I'm actually on the first cycle of I. So the first cycle of I means I to the first power, which is just I. So I know that I fifth is just I. I to the 6th, if I divide 6 by 4, I'll just get a remainder of 2. So we know that it's I to the second power, which is -1. And for this one, I to the 7th, I would do 7 divided by 4, which is 3. So it would be I to the power of 3, because 3 is the remainder, right? And we know that I to the power of 3 is -I. Same for this. 8 divided by 4 has a remainder of 0. So it's just, well, it's just 1. Because we know that whenever we have a remainder of 0, it's a multiple of 4. And whenever you have a multiple of 4 as the exponent, it equals 1. So I to the 8th power equals 1. Do you guys understand this? This concept of taking cycles of it and having it repeat every 4 times. Okay, perfect. So we're going to move on to this one, 284th power. Now, this seems like a huge number, and if we didn't know the technique, well, this would take forever for us to solve, right? But we do know the technique, and that is just dividing this exponent by 4, because every time it hits 4, all we get is a repeat. So if we divide this by 4, we can just do some long division, right? This is 0, this is 4, 1, 4, and a remainder of 0. And what happens when we have a remainder of 0, guys? Do you guys remember? Yep, it's just 1. So I to the 0th power is actually just 1. So we know that I to the 284th is just 1 because it's a multiple of 4 with a remainder of 0. So cool. Now we know how I repeats and how we can take exponents to I. So this will help us on one of our future problems. But for now, I'm going to introduce what we came here for, complex numbers. So complex numbers are always in the form a plus bi. And this has 2 parts. Part 1 of it is the real part. So a stands for any number and b also stands for any number or a constant. A is the real number, so it could be anything like 1, it could be 2, 3, it could be 400, it could be 3.4, right? 5, because this is a real number. It's a number that we can perceive, a number that we can count. But this part is the imaginary part. So even though b can be any number or constant, for example, this, for example, 3, as soon as we add this I, it actually becomes imaginary because I is not a normal number, right? If we square it, it actually becomes -1. So in complex numbers, a is the real part, and the second part is the imaginary part. So both a and b are real numbers, yeah. And another example of a complex number, or a full complex number, would be something like 4 plus 2i, for example. Or something like 6 minus 5i. Anything really works. This can also be fractions, right? It could be 4/5 plus 1/3 I, and this would be one number. This whole thing is one constant, but it's a complex number. So let's see how we can use complex numbers in arithmetic. So just like real numbers, we can perform different operations like before on addition, subtraction, multiplication, and even division. But I'll explain division later because it's a little bit more complicated. But the rules work basically the same as real number operations, except we know that I squared is -1, right? So for example, addition. If I wanted to add something like 1 plus 3i plus 4 plus 2i, for example. And remember that this is actually one number. We've just split it into its complex part, or its imaginary part, and its real part. But this is one number, and that is one number as well. And that's how we're going to treat it when we're adding. So when we add these, all we have to do is add the real part. So it's just 1 plus 4, which is the real parts. And then after that, we just add the imaginary parts, which is 3i plus 2i. 3i plus 2i. And since we're not multiplying these I, it actually doesn't become a negative number yet, because it only happens when we square I, right? So 1 plus 4 is 5, and then 3i plus 2i is just 5i. So we know that this plus this is just this. And then let's try subtraction. Subtraction's also very similar. So if we wanted to subtract this number from something like, sorry, we're gonna make this, let's make this 12i. So if we subtract it from something like 1 plus 8i, which is also one number, what would we do here? Well, we would just do 3 minus 1, 3 minus 1, and then we would do 12i minus 8i, right? So 12i minus 8i. And then 3 minus 1 is 2. 12 minus 8 is 4. We just add this constant back, and then this is our answer. Okay, so we're going to move on to the next page, and there's going to be some practice problems. So I want you guys to try out these operations, so number 1 and number 2 for yourselves, and see if you can figure it out. I'll give you guys like a couple minutes. Just try it out. And if you think you figured it out, feel free to type it out in the chat or unmute. Do any of you guys think you've got it? Any answers to number 1? We're just adding this and this. If it helps, actually, how I like to visualize it is I actually like to put it vertically down like this. So it's like we're adding two numbers like this. And this really helps me visualize it better. Okay, but if no one has an answer, let's just go over this real quick. And so 3 plus 2, right? Because when we do addition of complex numbers, we just split it up until it's real and its complex part. And in this case, its real parts are 3 and 2. We just add those together. 3 plus 2 is 5. And then we add the imaginary part together. 4 plus 19 is just 23. So the answer to this question is 5 plus 23i. Okay. Now for this second question, it's a minus, right? So we can set it up the same way. 5 plus 9i. And then we're subtracting this number. So let's just do 5 minus 2 for now. 5 minus 2 is super simple, right? It's just 3. Now, the second part is 9i minus negative 22i. And let me just write this down. 9i minus negative 22i. That's the second part. And you'll notice that we have two negatives here, right? Because we're subtracting a negative. And whenever we subtract a negative, all it is a positive. Because two negatives always make a positive, right? So 9i minus negative 22i is just the same thing as 9i plus 22i, which is 31i. So this would be the same answer, would be the answer as to this. So does everyone get this? I want to make sure that you guys are completely clear about this so that we can move on to the next one. Okay, no questions. So let's move on to multiplication. Now, multiplication is very different. We can't just do this part times this part and this part times this part, because now you'll notice that we have these parentheses. And I'm not sure if you guys have learned foiling, a concept called foiling, F-O-I-L. And basically we use this whenever we're multiplying something like this, right? X plus 1 or x times x times 3, or x plus 3. Whenever we do something like this, we can't just do x times x and then add that on to 1 times 3. That's not enough, right? We have to do a special type of multiplication called foiling. And basically foiling is when we take this first number and then multiply it to this number, right? So in this case, it's x times x, which is x squared. And then the next step is we take this number, we multiply it to this last number. So this was number 1, this was number 2. So x times 3 is 3x. Number 3 is taking the second number and multiplying it by this. So this is number 3. And then we add that on. 1 times x is 1x. So we add that on here. And then the last step is multiplying this by this. And then adding that onto here. So this would just be x squared plus 4x plus 3. I just want to know, have you guys learned FOIL before? I'm guessing not, but if you have, that would be pretty cool. Okay. No, that's perfect then. So I'll just explain foiling in more detail. Now, I know that some of us in our previous lessons, we've like demonstrated foiling, or we've just used it without quite explaining it. And I'm sorry that if you guys were a little bit confused back then, but I'm just going to explain foiling real quick now. So foiling, like I said earlier, is a method when you have something in the format of this, like two parentheses, and you have not just a constant number, but you have two different types of terms, right? One of these has a variable x, and one of these doesn't. Same with this one. And when you multiply these together, there's a special step that you have to follow. And that step is multiplying these two, the front two, that's number 1. You add that onto number 2, which is multiplying this first one with the second one. And then you add that onto number 3, which is multiplying the second one of this one with the first of this. And then number 4 is multiplying the last ones together. So what you're basically doing is you're taking all the possible combinations of multiplication and you're adding them all together, right? So ax needs to be multiplied with cx and d. And then b needs to be multiplied also with cx and d. And this is basically how distributive property works, right? Because if I had ax times cx plus d, this is basically ax times cx plus ax times d, right? Because that's how distributive property works. We have to multiply this number by this, and we have to multiply this number by this. But now that we have this b, we do the same thing as here, but then we also have to add on what we do with b, right? So step number 1, ax with this first one, ax with the second one, and then we move on to b. So b with the first one and b with the last one. So that's foiling, and that helps us solve multiplication problems when we have things that look like this. And you'll notice that these two also look like this. It's just that I replaces this x, right? So for multiplication problems in complex numbers, we also just do FOIL. So in this case, if we have something like this, what's the first step of FOILing? Well, we take this first number and we multiply it by this and this, right? So 1 times 1 is just 1. And then we multiply 1 by the second number. So 1 times negative I, which is just negative I, because 1 times anything is just that, right? And then now we finished up with 1, so we can put that aside for now. But now we have to work on this second one, and we have to do distributive property for this as well. So we have to keep adding on. So I times 1 is just I, and then I times negative I. Well, what's I times negative I? That's just negative I squared, right? Because we have two i's and a negative number in front. And what's negative I squared? Well, negative I squared is just negative 1, right? Because I squared is negative 1, and you have a multiplication in front of that. So this is just 1. So negative I squared is actually just 1. And if we notice here, this is negative I plus I. And what's negative I plus I? Well, that's 0, right? Because you're adding the same number onto its negative version of itself. So this is just 0. We can ignore this. So the final answer is just 1 plus negative I squared, which we showed is 1. So the answer to this question is just 2. And 2 is no longer a complex number. It's just a real number because it doesn't have I anymore, right? So does everyone get this multiplication? This is probably one of the most confusing things we'll do with complex numbers. So if you guys understand this, that would be perfect. Any questions? Anyone? Okay. So if we don't have any questions, I'm going to move on to this next problem, which has larger numbers, right? 21 times 11, 2i times 3i. Looks a little bit threatening, but we'll solve it now. So I'm going to write the equation out. And then let's get to FOILing. So how does FOILing work? Well, we do distributive property on each of these, right? So we do distributive property on 21 first. So 21 times 11. What's 21 times 11? You guys can use a calculator for this, or if you came to this class 3 weeks ago, I taught you guys how to multiply by 11, right? It's just 2, 3, 1. You guys don't have to memorize this. You can always do this with a calculator or write it down on paper. But this is 21 times 11. And then now we're going to do 21 times negative 3i. So 21 times negative 3i is just 21 times 3, which is 63. And we add that I in the end. And then now we add on the distributive property for this second part, which is 2i times 11. So 22i. And then we add on 2i times negative 3i. And the complex number part is always one of the hardest parts because that's when we have to deal with I and we have the problem of swapping negative numbers whenever we square I, right? So 2 times negative 3 is just negative 6. And then we have an I squared. And I squared is negative 1. So it's negative 6 times negative 1, which is just 6. So here we just add 6. All right. Let me erase these. And then now we can just put these together. So 231 stays, oh, actually 231 adds on to 6 because they're both the real numbers, right? We can add them together. And we can also add this imaginary number part, negative 63 plus 22, which is 41, I believe. Yeah, negative 41. So this right here is the answer to number 4. Do any of you guys have any questions? Actually, I'll leave that on. Anyone have any questions about this part and how I got to it? Any questions about FOILing? Because FOILing goes beyond just this lesson. Foiling is pretty important. You guys will use it a lot when you get to algebra, or when you get to algebra 2, I believe. No questions? Okay, let's move on then. So we've done addition, subtraction, and we've done multiplication, but we skipped one, and that's division, because division is completely different than normals. We need something called the conjugate, and I'll explain what that is in a second. For a complex number a plus bi, the conjugate is a minus bi, and it's often denoted with a long bar over its head. So basically, this like whenever this is the symbol for a conjugate. And here's some examples for a conjugate. So here's what we said earlier. The conjugate of this is a minus bi. And the conjugate of something like this would just be this. So do you guys see what I'm actually changing here? It's pretty simple, right? It's just this addition sign. And I'll show you what it does in a second. But can someone tell me what the conjugate of this is? 3 plus 2i. What's the conjugate for this? Anyone in the chat? Yeah. Well, that's okay. It's basically the same thing as what I did before, right? I just swapped this plus sign into a negative sign. So all I have to do is this. Now, this is just an arrow that I'm saying that this is the conjugate. This doesn't mean that this is equal to this, because it definitely isn't. But this is just the conjugate of it. And if this, for example, was a negative number, its conjugate would be 3 plus 2i. So again, we just swap the sign. And now I'm going to show you guys why the conjugate is so important. So when we're foiling, for example, if I have something like this, when we're foiling, we end up with something that we don't want. And it's the imaginary part, right? So if I do something like this, 2 times 3 is 6. How do we do this? We do 2 times this last number, distributive property. So 2 times negative 2i, negative 4i. And then we add on I times 3, 3i. And then we add on this last part, which is I times negative 2i. And since we have 2i squared, it's just the opposite symbol, so it's just plus 2. And then we can condense it into this. But realize that we actually end up with another complex number. We have another I. And sometimes when we're dividing, that's not what we want, because you can't actually divide by a complex number. Instead, what we have to do is find a way to get rid of this I. And how we do that is actually multiplying by the conjugate. So for example, I'm going to show you guys what would happen if we multiplied by the conjugate. So the conjugate of 2 plus I is just 2 minus I, right? I flip this sign. And now if I multiply, I get 2 times 2, which is 4. I get I times 2, which is 2i. I get negative I times 2, which is negative 2i. And then I get I times negative I. What's I times negative I? That's just negative I squared, which is negative 1, which is 1, right? So I add 1 to the end here. And now we can condense it. 4 plus 1 is 5. But then you'll notice that 2i minus 2i actually cancels out and becomes 0. So the answer is just 5, a real number, right? And we can perform whatever operation we want with real numbers because it doesn't have an I anymore. So if we work this out for any problem, if we multiply by any conjugate of the number, we'll always get rid of these i's and we'll end up with a real number. So that's why we use the conjugate, right? So does anyone have any questions about the conjugate, why we use the conjugate? Because for division, we have to understand that the conjugate is used to eliminate this unwanted I. No questions, guys? You guys all understand this? Okay, cool. So we're going to move on to an actual problem now for division. So all we have to do is we multiply the top and bottom of the conjugate by the conjugate of the denominator. And the denominator is just this bottom part, right? So in order to do this, whenever we have a fraction, as long as we multiply top and bottom by the same thing, the fraction stays the same, right? So here, if I want to get rid of this I, remember what we do? All we do is we multiply by the conjugate. And we do the same for the numerator, because whatever we do at the bottom of a fraction, we have to do the top. But now, since this and this are conjugates, we naturally know that on the bottom, I is definitely going to cancel out. And I'll just confirm this real quick. Whatever this is on the top. But the bottom is 3 times 3, which is 9. And then we have 5i times 3. But then over here, what our next step is just going to be negative 5i times 3, right? And if we have 5i times 3, which is 15i, and then we add on negative 15i, 15i minus 15i is just 0, right? So there's nothing in between. And then now we just move on to the last portion, which is 5i times 5i. 5i times, or sorry, negative 5i, which is just negative 25i squared, which is negative 25 times negative 1, just 25. And you'll see there is no more i's, right? There's no i's anywhere. We're just left with a real number, which is whatever the top is over 34. And now the top we can simply solve by doing normal multiplication. And the top sometimes may be left with I, but that's completely fine because I is still a number, right? This is still a number. It's just a complex number, and we can't use it to divide, but we can use it to multiply. So all we have to do now is multiply this top, which is 2 times 3, which is, sorry, let me clear the space. 2 times 3 is 6, and then 4i times 3 is 12i, and then 2 times negative 5i is negative 10i, and then this last part, negative 5i times 4i is positive 20. So let me just write this out again. It becomes this when condensed. And actually, another thing we can do with complex numbers is we can factor out like numbers, right? So 26 plus 2i, we can actually just factor out this 2. Because we know that if 2 times 13 is 26, and 2 times I is 2i, then this equals this, right? Distributive property again. And if we factor this out, we also know that the bottom is divisible by 2. So right now we're just simplifying the fraction. So we can divide the top by 2, which is this, and we can divide the bottom by 2, which is this. And this would be our final answer. 13 plus I over 17. So I'm going to write out another example problem because division is pretty complicated, and I want to make sure you guys really understand this, right? So let's solve this problem, okay? So what do you guys think I should do first? What's the first step in solving a division problem like this? Anyone? What is the first step? You don't have to actually solve it, just give us the step. Right, it says right here, right? What do we multiply by? Multiply the top and bottom by the conjugate, right? Oh, sorry. So we're just going to multiply this and this by the conjugate of the denominator, which is just flipping the sign. 1 plus 3i. And we have to do the same to the top. And by doing this, we already know that on the bottom, we're going to end up with a real number because we've canceled out the i's. And we can confirm this by actually doing it, right? What's 1 times 1? That's just 1. 1 times 3i is just 3i. So plus 3i. And then negative 3i times 1, negative 3i. And this last one is negative 3i times positive 3i, which is just positive 9, because negative 3i times 3i is just negative 9i squared, which is negative 9 times negative 1, which is 9. And don't worry, this process will get more intuitive as you work more with complex numbers. But for now, we can just write it out. So we can also just simplify this. This becomes 10, and the i's cancel out, right? This top is whatever this is. And now, since we have the bottom, all we have to do is do the multiplication on the top, which we already know we can do even though there's an I. So 4 times 1 is 4. 4 times 3i is 12i. And then we move on to this next one, distributive property. 2i times 1 is 2i. And then 2i times 3i is 6i squared. And 6i squared is just negative 6, right? And so this becomes 4 minus 6, negative 2, 12i plus 2i, positive 14i, and over 10. And again, we can simplify this fraction by dividing by 2 top and bottom, right? So if we divide the top by 2, we just get negative 1 plus 7i. And if you divide 10 by 2, what's that? That's just 5. So we'll see that dividing a complex number ends up with this. And even though the top is still complex, we know that we can do multiplication with the top, but we cannot do division with the bottom. And that's why this is a simplified version of the first one, right? So, do you guys understand this? All good? No problems? Okay. If not, let's just do one more before we go. So I'm actually just going to do this last one, which is what is the square root of I? And this is a bit of a complicated question, and it's not one that you'll usually come across, but let's go over it because it's pretty fun. So what is the square root of I? So the square root of I, we know that I squared is negative 1, but we don't know what the square root of I is, right? But let's just say, sorry. Let's just say we name this a variable, for example, x, right? The square root of I equals x, and we're trying to find what x is. So how would we approach this? Well, all we can do is we can square top, or we can square both sides. So we end up with I equals x squared. And I is basically saying 0 plus 1i equals x squared, because I is a complex number, and we know that complex numbers are made up of its real term and its imaginary term, right? So the real term doesn't have anything, so it's 0, but the complex term is just I, and it's just 1i, right? The 1 is hidden. And now we know that x squared also has to be a complex number. So we can say that 0 plus I equals this complex number where a and b are its own numbers. So a, this part is the real part, and this part is the imaginary part. We can say that this is this squared. So now we can do some algebra. For this, we're just squaring, right? So this is technically foiling again, but I'm just going to go through it real quick. And then b squared I. So this is this. Because if I square bi times bi, that's just b squared times -1, right? So negative b2 to the second power. And then I can then condense this or rearrange it a little bit into what I have here, plus 2abi. And this looks complicated, but in reality, it's just a complex number. It has its real parts, which are just this, and they're all real numbers because there's no I. And we have our complex part, which is 2ab times I. And we know that this equals this, right? And if we had something like, for example, 2 plus 3i equals, like, for example, a plus bi. In this case, what would a and b be? Well, they would just be 2 and 3, right? Because we know that this equals this. So a has to equal 2, and b has to equal 3. So in the case of this problem, all we have to do is match it. We know that this real number part is equivalent to this real number part, which is just 0. So you know that 0 equals a squared minus b squared. And we also know that this is a 1, right? This is the real number part, or the imaginary part. So 1 equals this imaginary part, which is 2ab, 1i equals 2abi. And by doing this, we know that since a squared minus b squared equals 0, we have a squared equals b squared, which means that a equals b, right? Because we just take the square root of both sides. A equals b, and they're equivalent. And by using this information, we can plug in this stuff into here. So if I take this equation and I divide both sides by I, we can just cancel out I. So we have 1 equals 2ab. I can divide both sides by 2. So ab equals 2. And we know that a equals b, right? So all we can do is replace b with a. So we just have a times a equals 1/2. So a squared equals 1/2. So let me erase this real quick. So from a squared equals 1/2, we can do the square root of both sides. So we know that a equals plus or minus square root of 1/2. So if a is plus or minus square root of 1/2 and a equals b, then we also know that b is the exact same. B is a square root of 1/2. And remember, we're trying to find what the square root of I is, right? We're saying that this equals x. And we're also saying that x is a complex number, a plus bi. And we know what a and b is, right? So we can just say that x equals, plug in this, plus or minus. And plus or minus, if you don't know, by the way, this just means it could either be plus or minus, like both work. And then plus or minus square root 1/2 I. And we know that x is square root I. So here is our answer. The square root of I is just square root of 1/2 plus square root of 1/2 I. Now, I'm going to confirm this by actually squaring our answer. So we said that square root of I is plus or minus square root of 1/2 plus or minus square root of 1/2 times I. So how can we confirm this? Well, all we have to do is square this and square this, right? And squaring this cancels that out, so we're just left with I. And then we can square this. So again, we're foiling, right? So what's square root of 1/2 times square root of 1/2? Well, that's just 1/2, right? And then we're doing the second part, which is, might help for me to write this out for you guys. So we're foiling, we're doing this times this, which is 1/2, and then we'll do this times this, which is 1/2 I, and then this times this, which is also 1/2 I. And then we'll do this last part. So square root 1/2 I times square root 1/2 I is just this, and then this and this cancel out, right? So we're just left with 1/2 I squared, and I squared is -1. So we're left with -1/2. And if we confirm, or if we put this together, 1/2 minus 1/2 is 0. And then 1/2 I plus 1/2 I is just I. And then we can confirm that this I does indeed equal I. So we know that this was the correct answer for square root of I. So again, I don't expect you to completely know how to do this. I just found this to be pretty cool and a pretty cool usage of I. And it's a good demonstration of all the concepts that we need to use when we're using I. But this was our introduction to complex numbers. I know, pretty complicated, but that's what happens when we deal with something that we usually don't see, right? I mean, the concept of I is pretty strange to us.